8.3 Dynamic analysis of two variable data. So the goal here is to analyze two variable data and account for the impact of outliers and hidden or extraneous variables. So once you know there is a correlation between variables in a correlational study, it is important to consider what outside influences, if any, may be present. Outliers and hidden or other extraneous variables can have a dramatic impact on a linear regression model, which may skew analysis and interpretation of the data. So what are outliers? Well, an outlier is a point that does not follow the trend of the data. So a point that does not follow the trend of the data. And we can also have hidden variables. So as outliers are on the data, on the graph of your data, hidden variables are not. So a hidden variable is a variable that affects or obscures the relationship of two variables that can result of two variables that can result in a false correlation or a kind of fragmented trend. Okay. So detecting outliers and hidden variables. So it is easy to spot an outlier in a scatter plot when it is very far from the trend of the data. But what about outliers? That might not be so obvious. So how do we determine if something is an outlier if it's not really obvious? Well, we do that by creating a residual plot. And creating this plot can help us identify some outliers. So I first define what is the residual. And the residual is the vertical distance between the data point's actual observed dependent value and the value predicted by the line of best fit. So I'm going to write that down here. So it's the vertical distance between a data point actual, or you can say observed dependent value and the value predicted by the line of best fit. So, and the value predicted by the line of best fit. And the residual plot itself is going to show, so shows the value of each residual, because your data has many different points. So each of those points is going to have its own residual. And that residual plot will show all those residuals graphically as the vertical distance from the horizontal axis. From the x-axis. Okay, so it's time for an example. Will an increase in recycling result in a reduction of landfill? The table below compares the mass of garbage and recycling for a town during a recycling campaign. So here I have a graph. Our recycling initiatives working. And then on the y-axis I have the amount of garbage in kilograms. And on the x-axis the amount recycled in kilograms. So here is our scatter plot with a line of best fit. And here are the data values where these data points come from. Now, you're going to be asked to create an Excel file on your own to create this scatter plot and line of best fit, and use that Excel file and analyze the graph and determine that linear model and the R-squared coefficient, correlation coefficient, I should say. Now, for the sake, so I'll ask you to pause the video here and do that. Now, afterwards, I'm going to give you now the actual models themselves. So kind of like a after the fact. So after you've done this on Excel, you should have a linear model that resembles this: y equals negative 0.4535x plus 248.27. Your r squared value would be 0.698, and if you took the square root of that, you would get 0.84. And because the line of best fit is downward, it's going to be a negative correlation, so it's going to be a negative 0.84. So it's fairly strong and negative. Strong because it's close to the absolute value of 1, and it's negative. So describe the trend. Is the linear model reasonable in this case? So I'm going to say as the amount of recycling increases, the amount of garbage collected decreases. So it makes sense to have a direct negative relationship. Okay, and so the R value of negative 0.84 confirms a strong negative correlation. And so I would say this is a very good model. This line of best fit is a very good model for the data. Okay, so moving on. Part C, interpret the residuals for the points 120 and 200 and 200 and 142. So to interpret the residuals, you are going to need the regression model equation. So y equals, let me write that equation down one more time here, negative 0.4535x plus 248.27. So what is the residual again? So I'm going to say the residual of 120 and 200 is the difference between the actual value of this value right here and the predicted value coming from the line of best fit. So what's the predicted value? And the predicted value, the y value, is going to be, if I substitute that x value, and that x value is 120, and I put that into the line of best fit equation, then the y value that comes out is 193.85. So I can say that the linear model predicts a mass of about 194 kilograms, while the observed y value was 200 kilograms. So what's the residual? So the residual is going to be 200 minus 194. I'm just now rounding this for simplicity, and that's going to be a residual of 6 kilograms. So the observed value is 6 kilograms higher than we expected. Okay. What about for the other data point, 200 and 142? Well, similarly, I'm going to calculate the predicted value based on the line of best fit. So if I use the equation, negative 0.4535 multiplied by x, and x this time is the 200 over here, plus 248.27. And that y value will equal 157.57. Okay, so if I round that, then the model, I'm going to say, predicts a garbage mass of about 158 kilograms, while the observed mass value is 142 kilograms. So the residual for this point is now actually negative. If I calculate it here, so the residual is the observed value, 142, minus the predicted value, 158, and that's equal to negative 16. Okay, and just to show you on the graph here, so 200, so that point, 200 kilograms, and that's my line of best fit point. And for the second one we analyzed, it was sorry, for the first one we analyzed is 120 and 200, so 120 is right about here, and the red point would just be right below it. Okay, so how do I always remember which one's positive, which one's negative? Well, the residual value would be a line drawn between the red line and the upper data point, which would be above the red line. It's positive. For the 200 kilogram case, my observed value is below the red line, so that residual vertical line would be negative. So that may be a helpful thing, visual to remember for the future. So what does this value mean? It means that the actual mass is 16 kilograms less than the predicted value. Okay, now how do I construct a residual plot? So here are some instructions on Excel on how to create the residual plot. So I'm going to ask you to pause the video again and open up your Excel or even Google's spreadsheets and follow the instructions to create the residual plot. Okay, so you should have created a residual plot that looks something like this. So everything has to be centered around 0. So you'll have equally distanced total sum of points above and below. So you'll notice that you have some residuals above here and some below. So is there any kind of pattern in this plot? Well, there is no clear pattern in the residual plot. The points generally appear to be randomly located above and below the horizontal axis. And this is normally what you'd expect to see for a good linear model. Just wanted to draw here the horizontal axis. Right there. Let me change the color as well. Oh. I'll draw another one. All right, perfect. There we go. Yeah, so equally, like you have a certain number of points above and below. And they're all randomly spread, so it doesn't look like there's a particular pattern. Okay, example number 2. So this table here shows the price for several used motorcycles of the same model and their age. So create a scatter plot again. So I want you to create a scatter plot in the Excel file using my table of values here. And tell me what the regression, R-squared, and correlation coefficient are. So I'll pause the video, give you a moment to do that. Okay, so assuming you have the Excel model, you should have found that the regression equation here is y equals negative 1.6782 x plus 14.493. The R-squared value would have also been calculated on that spreadsheet to be 0.5835. And if I took the square root of that value, I would have 0.76. And I have to recognize that this is a negative correlation, so I'm going to put a negative sign there as well. So because it's 0.76, the absolute value, it's moderately strong. And we have to say it's negative. Okay. So what does that mean? Well, perform a linear regression and correlation analysis and discuss the goodness of fit. Well, I'm going to say here that this line of best fit is not a good model. Why? Because we have some outliers here. It's a significant impact on the correlation. Okay, and the line of best fit itself, I should say. Like this line of best fit is dragged down because of this hugely far away outlier. Now, so the model does predict a new cost of about the same as the observed cost of a bike that's 1 year old, which isn't really which is not really realistic at all. So, I'm going to say it's not a really good fit model. Now, part C. Follow a similar process as in example 1 and construct a residual plot and identify any outliers. So pause the video for a moment, create a residual plot. Okay, so your residual plot should look something like this. And what do we notice here? Well, look at some of the factors that we could include here. Like accident history, any maintenance, Could be a dud, whatever, why would that outlier exist? Yeah, it could be a number of reasons. It could be a bad bike, could be an used bike, maintenance, whatever the reason could be. Um, we could get some extra outliers that can significantly impact the residual plot. In part D, repeat the regression and the residual plot with the outlier removed. What would it look like? Well, now you would get a line of best fit that's more reasonable. It fits the data much, much better. Okay, so it has a predicted new cost, which is more than a kind of used bike. So you'll notice the correlation coefficient now. You should get something close to 0. Negative 0.97. Very strong negative correlation. Okay, I'm gonna stop the video here.